So again, from a background perspective, cryptography is the science of keeping messages secure. So the four important questions about why would you maybe want to use cryptography, this will help us decide what particular algorithms and approaches we're going to take. So the first one, the obvious one most people are familiar with, is confidentiality. So when I want to protect data, either as it's stored or as it's in transit, I don't want people to be able to read this particular message. That would be confidentiality. The next would be integrity, and that's where I want to verify that the data has not been modified, so we'll look at some techniques for that. Authentication is just identifying and validating who a particular user is. Non-repudiation would be where a sender cannot later deny that they sent a message, so we'll talk about that in the context of digital signatures. And again, the classes I'm going to talk about are in system.security.cryptography. The demos I'm going to give you happen to be from an ASP.NET Web Forms project. That doesn't really matter where you're going to use it. I mean, these are .NET classes. I'm a web programmer. That's what my production website's been using since beta of .NET 1.0. So that's the context for where I'm showing examples, but these same techniques will be usable for other websites and even in general .NET programs. So some of the considerations when we talk about the cryptography is, again, what is your goal? That's going to help us decide what technique we're going to use. How much is your data worth? How concerned am I that somebody's going to get access to this data? What would it mean if somebody did? How long does it need to be secured? And then I listed out some threats. It's always important when you talk about security and cryptography that you think about what are the ways that someone might attack me and what things might I be concerned about. Am I concerned about the data while it's being transmitted? Am I concerned someone can read my web config? We'll talk later about how to encrypt sections of your web config. So if you are worried someone could read it, that would be your response. Dumping out memory, we'll talk about that later. Being able to modify pages or reverse engineer some of my assemblies. And of course, other considerations, we have our own company security policies we need to comply with, and also just general regulatory compliance like PCI standards, etc. So the idea is you want to have layered defenses, and the question as you consider all of these things is, how many are enough? How much work do I have to do? How many different techniques or blocks do I have to put in place to properly secure my information? The other main thing I want to focus on is don't write your own. So .NET has a lot of great cryptography classes available to you that have been tested. The chances that you're going to be able to successfully write your own encryption algorithms is quite low. So if you take nothing else from this talk, don't try to write your own cryptography. Take advantage of what .NET already has available to you. Next, we'll jump into hashing. So the idea with hashing is that you've got a one-way function which is easy to compute, but it's significantly harder to reverse. So in other words, if you look at the picture, I've got some text on the left side. The purpose of the hash function is it's going to run a computation on that particular string, and it's going to give me back a fixed length answer. So I saw the wording once where somebody called this a data fingerprint. So it gives me an idea of what the data on the left-hand side is. If I were to go change a single character in the message on the left, you'll see a drastically different hash value. So this technique, we're going to talk about where you would use hashing. Hashing is a good technique when it's okay to see things, but you don't want it to be tampered with. So I have no concerns if somebody were to read the message I have on the left-hand side. I'm going to use hashing functions to help me make sure that no one's tampered with this information. And I have a little note here. We'll walk through a demo on this. Be careful when you have a limited value range. So in other words, if I were to try to do just yes and no, there's going to be two hashes for that. I'm going to show you why you might have some problems with that and how you could deal with that particular problem. So let's take a look at some real quick hashing examples. So in this example, I've got some plain text here. This is a simple demonstration of hashing. This happens to be one of the cryptography classes that we're going to focus on today. So SHA-1 Managed is a .NET implementation of the SHA-1 hashing algorithm. So that's the particular algorithm I'm going to use in this case. One thing you'll notice as we use cryptography, .NET wants to do all of the cryptography libraries using byte arrays. So if you notice, I'm starting with a string. I need to find a way to convert that string into a byte array so the compute hash function can work on it. So there's lots of different encoding techniques that I can use. UTF-8 happens to be a popular one. So what I'm going to do is I'm going to use the encoding UTF get bytes function. And as you'll see, I'm going to pass in my plain text string, and I'm going to get back a byte array, which is what my compute hash function wants. Now in this case, the SHA-1 returns 160 bits. I put some of the math here for you, but there's 8 bits per byte, so I'm going to get back 20 bytes for this particular hash. So regardless of what my plain text size is, I know that when it comes out, it's going to be 20 bytes long. So this is the basic call. So I've converted it from a string into a byte array. I call compute hash. That actually runs the algorithm to compute the hash value, and it gives it back to me again as a byte array. Throughout the course, I'm going to show you different ways that you can do conversions from byte arrays depending on where you're going to use this, who you're going to send this to. So you'll see a couple different examples as we go through. One of the classes that I'm going to take advantage of here is called bit converter. And I gave a nice comment here about how it works, but it basically takes each byte value, puts it in a hexadecimal representation, and it's going to kick this back then as a string. So let's see what this looks like. So if we see on top, I've got the original string, and then I put what it hashes to. So again, this is just the string representation of the hash value for that particular plain text. So that's really basic hashing, and we'll see why you would want to take advantage of these techniques. I've listed here some of the hash algorithms. So if you go into System Security, and you can find the hash algorithm. This is the base class of all of the hash algorithms we're going to talk about. We've got different algorithms, MD5, SHA-1. MD5 has had some issues with people compromising it, so I'm going to focus on the SHA-1. And you've got different sizes here. I'm going to show you how I've also got a page included for you that you can look through the code example that will show you the difference in performance. So the end result is, let's pop over there quick. As you look through the algorithms, you just need to consider, how am I going to be using this? Am I concerned about cryptography's impact on my performance? So I put together just a quick test page you can see. I chose to do 10,000 iterations just to show you that it takes a lot of iterations to actually matter. But I've used all of the different techniques below, and it just dumps out some of the sizes. And from what you can see, we're talking 10,000 iterations in a matter of milliseconds. So most of these are very close to each other. So we'll talk later again about your concerns about how sizes and things I want to use, but you can use the best algorithm here without really any impact on your performance. So as you consider using this within your website, it's important for you to test this out and consider what kind of impact this will have on your performance. So let's talk about some practical examples of where would I use hashing. One good place to use hashing in a web environment is to create what I call tamper-proof query strings. So the idea with this is I want to protect the integrity of my query string. People know how to go up to the query string line and hack things into the particular address line and have your page particularly do things that you might not want it to do. So for instance, if you created a web page that had a customer number as an ID in the query string, and you've probably got sequential customer numbers, somebody could easily go up to the address line, see that you're passing in a customer number, change it to someone else's customer number, and if you're not careful, you're going to be basically spitting out all the information for a different customer, which obviously would be a bad thing. So the idea with the tamper-proof query strings is we want to protect that query string, and one good way to do that is to use hashing techniques. So I'm going to show an example of a hash-based message authentication code. So the idea is when I create my original URL with my query string, I'm going to compute a hash of the query string value, and then I'm going to actually append that hash value onto my URL, so that when you come back and hit that page, I can look at that query string, I can take the query string value off, recompute the hash on the server, and make sure that you haven't tampered with it. So this would be a way for me to make sure that even though I'm putting ID values on my query strings, you're not able to tamper with those and take advantage of them. And I'm going to show you here at the bottom why you want to use a key to ensure that somebody can't break into this particular algorithm. So let's take an example first. We'll just see how this works. So I've got a page here that's going to create a query string. We'll zoom in here. As I click this, you'll see I've got my normal use tamper-proof query string, and you see I wanted to pass A equals 1, B equals 2, and C equals 3. But to make sure that somebody couldn't tamper with that, you'll see I also put on this QTP val. That is the hash, computed hash of that query string. So now what would happen is if somebody came up here and said, well, I want to see what happens if I put in a value of 2 for A in this case. They're able to go adjust my query string, but when they hit enter, my code is going to fire and say, that doesn't match. So what I computed when I did the hash of this and gave you this URL, I know that you've tampered with it, so I'm not going to show you any of the information on this page. Of course, we got to deal with people that might be cheating, so what would happen if they just deleted the hash? Would the code check that? Yes, it does. So let's look into how you could take advantage of a technique like this to make sure that people aren't tampering with your query strings. So what I've got here, I've got my URL that I want to create. Now you'll notice one repercussion of this is maybe I could have done that all in markup before. Now I've got to actually run some code. So what I need to do is, here's the query string I want to attach. I need to call a function that's going to hash that query string for me and then append it onto the rest of this URL. So let's look at what that function looks like. So all it does is it takes the query string as a parameter, it puts on my separator, that QTP val, and then it does a compute hash like what we saw before. So let's just go look at that again. And what you'll see is I'm going to do the same steps. I'm going to convert that string into a byte array. In this case, what you'll see is instead of using just the SHA-1, I'm going to use a key, and I'm going to show you why in a little while. But the important part is I'm reading this key in from my web config. So again, we'll talk later about whether this is a good idea in your situation or not, storing something like this in your web config. But that's what I'm doing for this example. We'll show later how we can encrypt that data. But again, what I've done now is I'm going to create a hash, but it's also going to use this key value. So it computes the hash, and then it returns. In this case, I've got another way to do a conversion if you want to see an alternative. So here in this case, I'm using bit converter again. But what I've done now is I've created that query string and added it on. So let's look at what the page that receives the query string will do. And when you look at it, you don't see anything immediately like, where is this protection coming from? Where is this tamper-proof check being done? What you'll notice if you're familiar with the base page concept, every one of my pages on the website is going to derive from this base page so that I can put code that is shared across all my pages in one particular class. So if we come into the code folder into base page, you'll see it just derives from the normal system.web.ui.page. When the onload for this fires, then what it's going to do is it's going to try to validate the query string. And just to give you an idea, I put this in here, there may be times where you've got system functionality that's creating links for you that won't be adding on the proper hashing. So I gave you an example here of if you use the built-in ASP.NET Forms authentication, it's not going to automatically add the hash like I'm adding. So I'm just checking quickly. If you come to my Forms authentication page, I don't want to enforce the tamper-proofing on that page because I know that it's not going to work. But if we go look at what happens in this function, this is where the bulk of the protection comes in. So the first thing I'm looking for is if there's no query string, I might as well return. Then I get the entire query string, and I check, did you submit a hash? So is there a hash value on the query string? If not, then something went wrong, right? I want to make sure that I'm adding this protection. If somebody went and just deleted the hash value, I want to make sure that that gets caught. So the next thing I do, that I got the hash value that was originally computed when the link was created. Now I'm going to go pull off the current query string, recompute the hash again, and then compare those two values. So again, when the link was created, a hash was done on the server, and that was the value. Now that I've sent it to the client, and a client might have potentially tampered with it, I'm going to turn around and see, has anything changed on this query string or not? And that's what I'm doing right here. I'm just recomputing with a new query string, comparing to what was submitted. And if not, I'm throwing an exception. So again, this is what's adding the ability for me to make sure people aren't tamper-proofing with my query strings, which are very important for websites. Let's go back to here, and I want to show you why I used a key in this point. So if I'm an attacker, and this is important to think about when you're using your own security, if I came to this site and I noticed that you had this hashing added and I wanted to break it, how would I go about doing that? Well, what I would do is, there aren't that many hash algorithms that are available. I would guess that you're probably using a SHA-1 sort of alternative. So let's see, I'm going to take off this one and use SHA-1 just to get an example. So I can run this again, and everything would look visually okay. I can click this. If I'm an attacker, however, what I'm going to do is I'm going to say, well, I really want to put a value of 2 right here. So I'm going to go compute my own hash. Like I said, there aren't that many hashing algorithms. So I'm going to write a page like this. I'm guessing you're using SHA-1. This is what I want to have for a query string. You notice I put in the value of 2. So I'm computing my own hash here, right? So if I go do this, I'm going to go see what kind of value I'm going to get back. This is the new hash value. So now what I can do, I can go back to the page I was on before. Let me open this up. I've got a new hash value here that computes to using the value of 2. So let me change this now to a 2. You can see I just got past all of the protection you were trying to put in place. So again, the big message here is you need to think about how somebody might attack this, and the crucial mistake you would have made if you didn't do that was, just by using SHA-1, anybody can run that same hash algorithm. By adding in this extra level, we talked about how many blockades do I want to put in place to make this hard to do. I've added one more. By storing this key value on the server and making that be part of my hash function, I've made it that much more difficult for you as an attacker. Now if you want to try to beat my scheme, you've got to come out here, and you've also got to be able to gain access to my web config file and steal that key, because without that key, this particular algorithm is not going to function. You won't get the same hash values that you would expect. So just a good example of thinking through what you need to do, how things work, and how you need to secure things. Another common use of hashing is for hash passwords. So this is considered a best practice. It's been going on for years. I grew up with Unix environments, and back then what people were doing was they used to store the password file in the clear. What they did is they looked and said, well, we'll use hashing. Instead of storing the actual password in our password file, we will compute a hash of it, because we know that you can't really reverse a hash function. So we're going to hash your password and store that in the password file. And they were so confident about this in the early Unix days, they were willing to make that password file readable by anyone, because they said, hey, we're using hashing. Nobody's going to be able to break into this. Why don't we just store and make it read-only? The problem they didn't think of is people attacked this by doing what was called a dictionary attack. So if you think about it, a lot of people's passwords are just common words that are out of dictionaries, or combinations of their user IDs or their user IDs reversed. So what you can do to beat this initial attempt at security would be that you could take a dictionary, an online dictionary, run through it, compute the hash of every word in the dictionary. Now all I need to do is compare my hashed value to what's in the password file, and that's how people broke into this. So we'll take a quick look at how that works. So just to give you a quick example, I looked, say, in a password file and I saw this hash value. We talked about with hashing, I'm not going to be able to reverse that back and figure out what your password was. However, and I just used 3 examples here, if I thought your password was nothing, password, or secret, I can compute the hash of those, and then I can compare that dictionary of values I have, which are just hash values and the clear text, against what your hashed password was. So I'm going to run this. And what you'll see is even though I couldn't break the hashing, that's not the attack vector I took. I decided instead you probably used a dictionary word. So I just hashed all of the words in the dictionary, and I was able to compare and find out what your actual password was. So how did people respond to this? Well, the next thing they started doing was adding salt. So the idea with salt was you need to add some unique random data to each password. So this greatly increases the work required. So what they did is they went for each password that was in the password file. They also created a little piece of random unique data called salt. They store that salt in the password file. Now, what happens is, if you think about it, it's made it harder for me now to do a dictionary attack, because now I can't just pre-compute all the words in the dictionary because there's all this extra salt values. It becomes computationally very difficult for somebody to break and run this attack against your password file. However, if you look at the note, if you think about what just happened, I can still go in the password file and see the salt. Well, if I were attacking your system, I'm going to go in and look for admin or administrator, see his salt value. I'm going to then just pre-compute my dictionary using that salt because that's a very high value account that I want to break into. So it did protect us against people mounting dictionary attacks against all of my passwords, but it really did nothing to protect my particular password. So we're going to look at another way that people deal with this. So what I've got here, I've got a function that just shows you I'm going to compute the hash with your original data. I also generated some salt, which is just going to be some random data that I'm going to add on. But if you think about the attack vector I just said, I could put one more hurdle in place, and they usually call this entropy, just some additional random data. In my case, I hard-coded it here. I could place it in my web config and encrypt it. Again, there's different things depending on what I'm concerned about. If I do put it directly here in my source code, what I would be worried about is if anyone ever gained access to my actual code behind assembly, you'd be able to use the reverse, the disassemblers essentially, and look and say, oh, now I can see what this is. So again, you need to think about how you want to store this. But in this case, by doing this, let's go see what happens. So I've got my original word up here, and as I hit Control F5, you'll see if I did nothing but normal hashing, this value here is going to stay the same. By generating a salt, you'll see the salt is changing, but I also like adding that one extra piece. So modern systems today don't just do salting. They also use techniques like this, where they're storing extra stuff that you don't know. So again, the hurdles become very hard for you. For you to be able to break an individual password now, you need to gain access to my code to figure out what is this extra random data. You have to find my salt, and then you can go compute all the hashes against your dictionary and see if you can pick my particular password. Let me just go check here quick. So let me come back to some of these. And again, one of the questions, I'm sorry, since I wasn't recording at the beginning, I am making all of this code available to you. I talked to the conference organizers, and they're willing to put this on the website. So I'm going to turn in the slides and the code for all of this, so you'll be able to look through this at a later time. Just to show you hashing in ASP.NET, here are some of the different places that ASP.NET itself takes advantage of hashing. So if you're familiar with view state, if you're a web forms programmer, all your controls are storing data into the view state. They actually add a hash on, just like I was showing for the query string, and so that's called the MAC. So if you've ever gotten the error of your view state MAC didn't validate, it's because when it sent it to the client and got posted back, something happened to that view state. And again, they use this, they're not trying to protect, in this case, what the view state looks like or you being able to see it. By adding this MAC or this hash to it, all they're saying is you're not going to be able to make a change to view state without me knowing. So you can't tinker with some of those values and affect what's going to happen on the server. That hash value will be detected and it'll be stopped. So that's an introduction of hashing and some places that we can take advantage of it. I want to talk about, now we're going to get into encryption, so I want to use some of the standard terminology. So the first one is plain text is your original data. Encryption is your process of obscuring that data. Once you've obscured it, it's called ciphertext. And now once I've encrypted it, ciphertext is what that data would be called. I decrypt it, obviously. Then the cipher is just the algorithm using to perform the encryption and decryption. So the first type of encryption I'm going to talk about are symmetric algorithms. The idea with symmetric is, based on the name, it's the same key used for both encryption and decryption. So I've named it secret key because that's what you want. By keeping that key secret, people won't be able to decrypt my data. So if we think again from an attacker's perspective, the best way that people will try to beat a symmetric algorithm is they're just going to try to brute force your key. So there's a certain, your key is a certain size. We'll talk about sizes later. But by picking a large key size, you've made it exponentially more difficult for someone to just guess what your key might be. They're going to start with all the combinations and try to decrypt your data. So again, when we talked at the beginning about how long does your data need to be secured, how valuable is your data, my general recommendation is going to be pick the biggest key sizes you can if it doesn't affect your performance. So I showed you how performance earlier wasn't really impacted much by the size of the hash algorithms. Something worth looking at from your perspective, but in my seat, I want to use the biggest key I can to make it as difficult as possible. So when you look at the picture there, you'll understand that the difficulty with a symmetric algorithm is how do I exactly distribute this key. So in other words, if I'm working with someone else online and I say, hey, I suddenly want to send you some data, it's great that we have symmetric algorithms, but the problem is how am I going to securely give you that secret key, right? That's really the Achilles heel of symmetric algorithms, so we'll talk about that later. There's a number of classes that are built in to .NET. I'm going to talk about Raindoll, the AES encryption algorithm. This is the government approved way of doing encryption, so that's the one I'm going to show in this case. The .NET symmetric algorithms are called block ciphers, and all that means is it's going to take your data, it's going to split it up into your block size of data, and it's going to run the encryption on a block at a time. So it does the first block, then it does the second block, etc. So if you think about the chance that your data falls exactly on your block size, in other words, the likelihood that it's exactly 256 characters, for instance, is not very high. So the first thing we need to consider when we look at symmetric algorithms is, in order for these ciphers to work, how do I pad out the rest of that empty block? So in other words, I've got a piece of data that fits in a block, but it's not up to the full block size. How do I want to fill that in? And you've got a number of choices. You can use just pad it with zeros. You can pad it, that PKC27 says pad it with the amount of size that's left, like how much room is left that wasn't filled. What I recommend instead is the ISO 10126, which is basically fill it with random data. So we'll talk about, when you talk about cryptography and security, generally randomness is your friend. So I recommend that you use that one. I'm going to show you when you don't use that one what can happen. But that's padding. The mode that the cipher runs in, there's two different modes that it can run in. ECB, and all that says is I'm going to blindly take a block of my plaintext, run the cipher on it, and then get the encrypted data. What CBC says is let's add a little more randomness into this. Let's take a block, encrypt it, and then use that encrypted information as input, some additional randomness into when I do the encryption of the next block. So essentially, as it goes block by block through your data, it's using some of the information from the previous block to help make it more random. So again, that's the one I recommend, and I'll show you again why you want to do that. The last thing you need to know with symmetric is it's got what's called an initialization vector. So if you think about the CBC mode I was just talking about, what would be the random data that would be used to encrypt your first block? That's what the initialization vector is. So it's just a piece of data that's used to help seed some randomness into your first block of encryption. I'm not a cryptologist. I don't know why this next statement is true. I just know that it is. It does not need to be secret. So when I do symmetric algorithms, what I'll do is I'm going to encrypt the data. I've already gotten you the secret key somehow. I'm going to send you both the data and the initialization vector. Those two pieces of information are needed for you to be able to do the decrypt. And again, the initialization vector is not something that needs to be kept secret. However, don't ever reuse the initialization vector from one encryption to another. It's meant to be something random that you generate right now and send to whoever needs to see this data. If you start to reuse the initialization vector, you've lost some of your randomness. It makes it easier for people to see patterns in your data and figure out how to break into what you're using for your cryptography. So let's look at some symmetric examples. So again, I am including the system security.cryptography namespace. So I've got a method here that's going to create my cipher just to make it easier for me to reuse. We talked about I'm going to use the Raindoll manage class, which just means it's a .NET implementation of the Raindoll algorithm. I'm going to pick the key size of 256 and a block size of 256, which is as large as I can go. I'm going to use the two recommendations I stated. I want the padding to be extra random data, and the CBC again is saying use the previous block's encrypted value as input just to add some randomness. In my case, I stored my secret key in my web config file. And then, so what I've done is I've now set up the cipher algorithm. So to do an encryption, I'm going to create that cipher just like I did before. When I create that cipher, it's going to create a random initialization vector. So I'm just using, in this case, base 64 to convert it from a byte array to a string so I can show it on the screen. So I showed you earlier how you can convert it to hex. In this case, I'm just using base 64 to show you a different example. I create my encryptor. Just as we saw before, cryptography algorithms need to work on byte arrays. So even though I have a string, I need to convert it. So let me show you quickly what the page looks like. So if I come in here and type in something, let's say aspConf, and do an encryption. Again, this is my ciphertext. That's the encrypted data. Here is the random initialization vector. So these are the two pieces of information that I would then send to whoever I want to be able to read my information. Once they receive those two pieces of information and they already have the secret key on their end, they can do the decrypt and get back to where we started. So this is kind of the example we're walking through. So again, I just converted the plain text I want to encrypt. I used the UTF-8 again and got a byte array. All I need to do then is call transform final block on that plain text. That's what does the actual encryption. It's going to give me back a byte array with the encrypted data, and I just use base 64 again so I could show it on the screen. So that's how easy it is to use a standard, well-implemented cryptography algorithm for symmetric. And by the way, when I didn't show the example here, but I do have an example of how you can actually create keys. So if you look at this get bytes, depending on what your key size is, in this case I had 256 bits, so I used 32. This will get you some random data to use for a key. So I went through that process, stored it in my web config. Again, came back here, did my encryption. If I were on the opposite end, what I would do is I need to take the IV value. Again, that's just the random data that was used for the first block. Put it into my cipher as the initialization vector. And then I'm going to create my decryptor. In this case, I sent it to you as a string. So you're going to unbase 64 it because that's essentially what we agreed to encode it with. And then you'll do your decryption. And then again, in this case, we know that we agreed to use UTF-8, so that's how I'm going to convert it from the byte array back into a string. So that is basic symmetric algorithms. And again, these are useful if we have given each other our keys and the distribution isn't a problem. Symmetric is very fast. So let me change the mode. I want to pop in here and show you what it does if you use the other two modes. So if we go hit this again, we'll see every time I hit this page and do an encryption, you'll see how the value of the ciphertext is changing every time. If I were to go back into the code and use the other techniques, I told you I would show you why I do it this way. If I chose the poorer padding and the ECB mode, let's build this again, and we'll hit that page. Let me actually close that one. You'll see every time I'm doing this encryption, you notice how this is staying the same. And again, that's just the disadvantage of it when I did the zeros and the ECB instead of the better two modes above. All it's doing is, as I'm transmitting data, people are going to be able to see this. Let's say I only had, I'm sending to somebody either a yes or a no answer. As I'm transmitting this data, if it's the same every time, somebody's going to pick up pretty quick that there's only two particular values, and if they can figure out how I'm reacting on the other side, they can eventually figure out I'm saying yes or no. So it's just a good idea to not use these two and to use the two that we had above, just to add some extra randomness into things. I won't spend a lot of time on this example, but if you're used to using streams in .NET, be aware that there is a crypto stream. So you're actually able to integrate your encryption and decryption work into your streams. And so we'll show you again, you'll have access to this code, but I'll show you quickly how this would work. We got the same basic setup up here to create our cipher, so I won't go through that. What's different down below is if I'm using streams, I can actually chain my particular tasks I'm going to do. So I know I want to encrypt the data, I know I want to base 64 encode it, and then I want to write it out to a file. So if I'm using a file stream, I can also get access to a base 64 transform, and I can set up my cipher transform. Then what I can do is I can create some streams below here, so you'll see the files at the bottom. Writing to the files is the last thing I want to do. Right above it, I want to do base 64 encoding. And then as I set up my second stream, I'm going to put the cipher on the top. So now what I've got is when I call my normal stream write, It's going to do my cipher transform, which will do the encryption. It will then base 64 it, and then it will write it out to the file. So if I did this and set this all up, I could continuously use this stream. And if we go look at what this looks like, you'll see there's an output file, and I've got encrypted data in there that's been base 64 encoded. So if you do a lot of streaming work, you might want to take advantage of the crypto streams. It's an easy way for you to take advantage of adding cryptography into your stuff when you're using streams. Some places that it does symmetric encryption in ASP.NET, again, ViewState by default is going to use encryption. And so what that does is not only can people not tamper with the data that's sent down to the client, but they can't see it either. So let's take a look at an example of this. So I've got some particular data. Let's say I'm storing some secret data in my view state. Right now I've got, in the web config, I've got the view state encryption mode set to never. So let's just pull this up and see what we see. If I did this and I looked at the view state value, I could pull this value out. And if you've seen this view state decoder before, Fritz Onion created this a while back. I can paste in a view state string and decode it, and voila, I've got secret data. So the first message is obviously this is going to the client. View state is you don't want to put secret data in here because there's tools like this that would let you actually do the decryption. If I were to come back in here and set this to always and do those steps again, what you would find is as it got sent to the client, it actually encrypted the view state data. So now if I took that data and tried to paste it into the view state decoder, it would actually fail. So it's just a good use of where is ASP.NET taking advantage of things like symmetric encryptions. I've listed up some other places here as well of where it takes advantage of cryptography itself. Now we'll talk about asymmetric algorithms. So we talked about the secret key or symmetric earlier. The idea with asymmetric is there's going to be two complementary keys, a public key and a private key. So each person that's going to be involved in using this type of encryption is going to create their own keys. One of them is meant to be public, that they share with other people, and the other one obviously is private, which you don't want anyone else to see. They use this because it makes the key distribution problem go away, or it lessens it tremendously. So now what I need to do is if I'm working with a partner that I want to send data to, all I need to do is accurately get their public key. And so we'll walk through how the algorithm works. But the issue with this is that they're generally about 1,000 times slower than symmetric. So what I gave an example here of if you want to take advantage of key distribution but still be fast, what people usually do is they will create a symmetric key on the fly to use for a session, a communication between you and a receiver. But to pass over that secret key, they'll use asymmetric encryption. So let's take a look at the picture here. So you've got plain text coming in. If I had a particular person on the internet I wanted to send the data to, that would be the receiver. They would give me their public key. The way asymmetric works is the public and private key are inverses of each other. So whichever one you use, the other one is the one that will undo it. So if I used the receiver's public key and encrypted the plain text, the only thing that will decrypt it now is the receiver's private key. In theory, they're not going to give that to anyone, and they need to keep that secure. But in this case, then, anything I wanted to encrypt, I would always use their public key, and again, they would use their private key to do the decryption. So there's a number of classes. I'm going to demo using the RSA classes. So let's look at what an asymmetric would look like. So again, you need to create your keys. I didn't mention it before, but I'll mention it now. I've got a script text file in here that shows all of the commands that you want to use when it comes to RSA, like how do I create keys, how do I export them, how do I show them, how do I move them to another machine. So as I refer to steps that I do, you can come in here and see the examples of what are the correct ways to go create keys, for instance. So in this case, I created a set of RSA keys. I exported it and got an XML representation of it, so I chose to just put it here as a string. It's just some XML. In this case, it stores the particular keys. So again, I've left a lot of different examples in here. There's lots of places I can store my public and private keys. There's a machine store built into Windows. Again, I chose to do it as an XML here. So I left them in here, commented out, just so you can see you have different options for where you want to store these things. And again, here's an example using it from the web config file. But what I'm going to do is I'm going to pull out the particular keys so I can show on the screen. So let's see what this guy looks like first. So if we look, I've got some plain text. I'll do the ASP conference 2012. I'll do encrypt. You can see I've got some ciphertext. I just chose to display my keys down here so I knew what they look like. If I do a decrypt, get my cursor off of that there. All right, let's get out here. Let's try that again. I do the encryption, I do the decryption, it gets back like you would expect. So when I need to do the encryption again, I'm going to create my cipher, which I've got above here. I just use the RSA crypto service provider, and again I use the XML file for my keys. To do the actual encryption then, again I take the string, I convert it into a byte array, we've seen that. And I just need to call the encrypt function passing in the data. And then again, I use base 64 here just so I could display it on the screen so I could get it back to be a string. In this case, the decryption again, I'm using the key pair I have above. So this is going to be using the private key. It does its decryption, and then it gets it back out so that it can show it as a string again. So this is the basics of doing encryption and doing decryption with RSA. So where would this be useful? Here's a good example of if you think, say you have a website, you need to take credit card data, right? You need to be compliant. If you start to think about which one of these algorithms would be better for this, I could use symmetric, and every time I took a credit card, I could encrypt it. The problem is then I need to have a key. Right? I need to have some key to do the encryption so that whoever needs it later can do the decryption. In general, I don't like to store keys like that on my public-facing web server. So in other words, I'm afraid from a security perspective that if someone gained access, became an administrator by hacking a web server, they would have access to all of the files. They'd be able to find this particular symmetric key. So instead, if I look at it and say, well, why don't I use asymmetric with a public-private key? The idea is if I generated an RSA key pair, now I've got a public and a private, I'll store the public on my web server. In other words, I'll put it in my web config, I'll put it in my code, it doesn't matter. If somebody found this, there's no real risk to me because the public key is something I would normally let people see. The only way, once I get the credit card number and I encrypt it, the only person who can decrypt it now is whoever stores that private key. So if I put that private key then internally inside, not on an internet web server, behind firewalls on a machine that I consider secure, if no one else can gain access to that private key, now this would be a good approach because I'm able to take the data. I don't need to worry that someone's going to get my key. As soon as I encrypt it with my public key, now I know the only person who can decrypt it is the person who has the private key. So I'll show you an example of how this could work. So in this case, here's a page that's internet facing. I'll just put something and I encrypt it. Now I could store this in a database. I could do whatever I want with it. Again, this is my public-facing website. I only have my public key. Some internal system then would have access to my private key. So I could take that cipher data, and I would then be able to decrypt it. So let's look at how this example looks in code. So I generated an RSA key pair again, but in this case I only exported the public key. And that's what I'm storing here again as just a string. The encryption looks exactly like it did before. I just create the RSA crypto service provider. I use my public key from the string above. I do the encryption, the base64 encoding, etc. But again, the nice thing is there's nothing stored now on my public web server I need to worry about being compromised. Internally, I've exported both the public and the private key, and that's what's represented here. And I do the decryption like I did before. But this would be a good example if I think of my threats, think about how people might attack me. Taking advantage of asymmetric makes it where I don't need to worry about exposing my secret keys on my public-facing web server. So let's talk about digital signatures. So the idea with a digital signature is I want to provide integrity and non-repudiation. So in other words, if I were to send data to you, I want to make sure that it hasn't been tampered with, so that when you receive it, you know that it got transmitted okay. You also want to know that I'm the only person who could have sent the message. So if we look at the picture below, another note here, by default, when you talk about digital signatures, they're not assuming that you need to encrypt the data. I'm going to kind of do the mother of all demos here now for cryptography and do all of that in one. It's going to use hashing. It's going to use asymmetric. So in the picture, what you see is I've got some plain text that I want to send to someone. So the first thing I want to do, I don't want people to see this data, so I'm going to encrypt it using the receiver's public key. So again, what will happen is as soon as I finish encryption and I get the ciphertext, the only person who can decrypt it and see that is the person who has that private key. So that would be my receiver's private key. If I then computed a hash on that encrypted data, now I've got the case where I've got the encrypted data no one can see. I'm tacking a hash onto it so that when I send it, the receiver can check the hash value and make sure that it hasn't been modified. To prove that it came from me, I'm the sender. I'm going to sign it with my private key because I know my partner has my public key and they're reverses of each other. So when we look through the code, if they're able to reverse my signature, they know that the only person who could have possibly signed that was me with my private key. So let's take a look at this example. Close a few things here. So I'm going to act like the sender here. I've got some particular data that I'm going to send. So I'm going to, in this case, I'm just pretending I have a partner and I want to access something on their website via URL, so I want to pass some secret data to them. So if we look up here on the URL, you'll see I've tacked on a secret. And if I were to go further in the query string, you'll see I also tacked on my signature. So that is the encrypted data I wanted to send you. That's what's in the secret. The signature has the hash value that I signed, so you can make sure that it's from me. So you can see as I got over there, the data was transmitted to them. So let's look at how this looks. What I need to pull this off from the sender's perspective, I need the receiver's public key because that's how I'm going to encrypt it, so only they can see it. I'm going to use my private key in this case, so I've got both of them here. I do what I did before. I create a cipher. I'm using my sender keys in this case. For the receiver, I'm using their public key. Here's the data I want to transmit. Just like we've done through the whole session, I need to convert that from a string into a byte array. So you'll see me doing that using the UTF-8. So the first step, again, I want to encrypt this data so only the receiver can see it. So I want to use that cipher because it has their public key. Once I encrypt that now, the data I want to send is securely encrypted for confidentiality. No one else who intercepts this can actually see it. So that was my first step. Then I want to compute a hash of it, because by hashing and attaching that, the person who receives it will know that it hasn't been modified. Now, there's some extra classes around digital signatures you'll see here. So I tell it I want to use SHA-1 in this case. I was kind and didn't do the HMAC version of that. So I can create a signature now based on that hash. So I encrypted the data. I computed a hash of that encrypted data. What this is now doing is it's taking my sender's private key and signing that hash value. And then you'll see I'm base 64 encoding it so that I can attach it to my URL. You'll see down here I've got the secret and I've got the signature on my URL using URL encoding. On the receiver end now, it's just going to be the reverse of this. They're going to need both of their keys, but they only have my public key as a sender. So I've got some basic checks in here. Did you actually send the secret? Yes. Did you actually send a signature? Yes. I unbase 64 of those, so I get back the original encrypted data and the signature data. I take the original data, I'm going to recompute the hash again, right? And then I can go through the steps down here. The signature classes, again, will do the work for me, and they'll verify the signature right here. So the signature bytes that were sent compared to the hash that I just computed, and did it for sure come from me, is all incorporated in these lines. So you've got a lot of power there, making sure that nobody modified that encrypted data and that it definitely came from me. You have my public key up above that will reverse my private that I used to sign it with. Then now that I've done that, I've ensured that the data hasn't been tampered with. I know it came from the sender. Now I'll just do my normal decryption, and I have the data that you would expect. So again, it's a very involved demo. There's a lot of details going on here, but if we go back to the high level of what we're trying to accomplish, again, we're trying to encrypt it first using the receiver's public key. Then we're going to compute a hash. We saw how hashing was useful to make sure things weren't tampered with. And then the key for digital signature, we're using my private key to sign that hash value, and that becomes the digital signature. So that's the basic encryption things. We'll step now into how can you protect your config sections. So in your web config, it's possible to encrypt sections of your web config. There's certain sections that don't work, but the one that you'll generally do it on is your app settings. The nice thing is, in a way, it's auto-decrypted for you. So I'm going to show you that once I encrypt the data, the rest of my code doesn't need to know that it was encrypted. ASP.NET on the fly will do a decryption for me, which is handy. The only concern, again, if you think about threats, if somebody could modify my web page on the server, they'd be able to call these accesses to the web config, they'd be able to see the decrypted data. So you just need to think about your risks again. There's two ways to do this. One is using DPAPI and one is using RSA. DPAPI is interesting. It's keys that are built into Windows since Windows Server 2000 and XP. It's great because I don't have to worry about key storage. It's kind of an auto-created key for me on that server. The bad news is if you think of a production web farm, I've got my machine, my dev my test, my stage machine, my production farm. This key is specific to a server. So essentially in a web farm, this isn't going to work. So I'm not going to spend time on it. You can look at the examples if you want in that script file. I'm going to focus on what you would actually do in a web farm, which is encrypting with RSA. So the first thing you do is I'm on a given server. I would generate an RSA key pair. I need to set up my local web config to know about that key pair. I will encrypt my web config using the ASP.NET Reg IIS utility. I'll grant access to the key for the right ID, and then I will export that key pair. So I've gone on one server, created a key pair, I encrypted my web config. Now what I want to do is as that web config moves to my stage server and my production servers, I need to go to each of those servers and import that same key pair so that it knows how to do the decryption. So let's take a look at how this works. I'll go in that protect script. You'll see down here I'm going to actually encrypt using ASP.NET Reg IIS. So if we go on web config, again, some of the setup, I needed to create the keys, and I needed to set up this protected data section to say which keys I wanted to use. Now I'm going to kick off a command prompt for Visual Studio because that has access to the ASP.NET Reg IIS. So now what I'm doing is I'm saying use the ASP.NET Reg IIS, and I want to encrypt the app settings section and the web config is here at this path, using that custom provider so it knows which keys to use. So if I scroll up, you'll see app settings is visible right now. If I were to kick this off, it tells me it's succeeded. I come back to Visual Studio. It tells me I need to reload. Now you'll notice my whole app settings section is encrypted. So again, as we talked about threats at the beginning, do I need to do this? Am I concerned that somebody would have access to a web config that I don't want them to see this data? If so, this would be a technique I could use. If I look at this page, again, once you've done the encryption, the good thing is that you use your normal access to your app settings, and it will automatically decrypt. So when I go and kick this off, oops, pull this up. Remember where I did that here. I don't know why that's not working at this moment. Let me decrypt again here to troubleshoot that one. But trust me, it generally works. Again, the idea was I would be able to, I don't know if I was playing with my keys, I don't know if I took away access. I'll decrypt that again. And we'll see that it comes back. So the idea again is if you need to protect your web config sections, you're able to use this with RSA. It works fine in a web farm because it's going to be the same key. So I just generated a key, did the encryption, moved the key to each of my servers, and then granted permission so that IIS can see those particular keys. And again, what's supposed to happen when I pull this up via Web Configuration Manager, it transparently gives me that data back. So again, the good news is if I'm worried about people reading my web config, this could be a good solution, one more hurdle for people to get over. The bad news is that if someone were to actually look at my source code and put their own pages on my server, they would be able to have it kick the data out. So if it knew that there was an RJB, they would be able to see it. Lastly, we'll talk about key sizes again. So the size of the keys that you use for the algorithms are really a trade-off of performance and security. And again, in my seat, what I'm doing, I would do the performance testing in your particular app in case you have a situation where you're encrypting an awful lot of data and it doesn't work. But I would err on the side of using the largest key size that you can because it's going to make it exponentially harder for somebody to try to brute force your keys. At the bottom, I listed out some key storage. So we talked about the safely encrypting credit card data. Maybe a good approach is to make it where storing a key is not an issue. By using asymmetric to encrypt that credit card number, I didn't need to be concerned about where can I put a secret key on my web server that I'm not worried about. So when you store keys, I showed you if I put a key directly in a string, somebody can use a disassembler and just kick out and it will show them exactly what that value is. So am I concerned that somebody could actually gain access to my code behind DLL? That would be somewhat difficult, but if I were concerned about that, then storing it in a string is probably not a good idea. I could put it in an encrypted app settings section, and then I could also get a lot more funky if I wanted to and break that key up and store some of it in code, some in the registry, some in config files, and just kind of repatch it together. So again, how crazy you get or how paranoid you are about your particular data and what your threats are will guide how you want to have your keys stored and whether you should have it on the server at all, where you should put it, and what sort of blocks you have put in place for people needing to gain access to your keys. Quickly about other .NET cryptography, there are some digital certificates classes. If you've looked at the enterprise library before, there is a cryptography block. Honestly, I haven't used it. I've felt that the base .NET classes have been pretty straightforward to use, that I didn't feel the need to use the enterprise library, but that's available. The last ones are somewhat interesting. We talked about if you're worried about people dumping the memory of your web server. So if you took a credit card out of a text box, you did the encryption, and you're worried about, well, I don't want to store something in session or cache or in my memory that somebody could see. You could use protected memory, protected data, secure string. The idea with those are that they encrypt in place in memory. So if somebody then took a process dump of your web server, they wouldn't be able to see that. The bad news is those are great, but there is a time period in transit. I have to get it out of a text box in ASP.NET to put it into one of these. So temporarily, that's going to be stored in a string anyways until my next garbage collection occurs. So just be aware these aren't perfect, but they are an improvement as far as being able to secure some data that you have in memory. So in summary, main message, don't write your own cryptography. There's good implementations in .NET. You'll end up making mistakes. There's a lot of things you need to think about, so please don't write your own. Use trusted algorithms and implementations. Again, think about what you're trying to protect. Use hashing if you want to validate that the integrity of your data hasn't been changed, or if you want to prove you both know the same secret, like what they do with passwords. In general, use symmetric algorithms if you can, because they perform a lot better unless you have special needs for asymmetric, like digital signatures, etc., or a key distribution is difficult. And again, know your threats, choose the proper countermeasures. That's my blog, my email, Twitter information. Again, I'm going to turn in the code and the slides. I do have a little bit of time left for questions, so I'm going to pop over here to Q&A and see if there's any that we can hit quickly. So what would be the best way to implement this tamper-proof URLs if you're using jQuery to making a GET call? I'm not sure what you would have in jQuery as far as cryptography algorithms. I've never tried doing client-side cryptography with those. So the issue with that would just be you would have to have an implementation essentially on the client if you want the client to create the URL. If you know who you're going to call using the AJAX, I think you'd still get by with it. On the server, you would generate the right URL to use that had the right tamper-proofing. Pass that to the client. It's fine that the client is making the call using jQuery with AJAX. That wouldn't matter if the server was being okay and creating the URL for you. So I don't know if that answers the question. If you actually had to generate URLs on the client that had tamper-proofing, you'd have to find a library, and then I would be concerned that people can see the code you're using to compute the hash, and it would be easier for them to break into. By using the techniques I showed before, you'd probably want to do server-side with a key and give it back to the client if that was possible.
Hey, Robert, this is
Yes.
Rich. Flip over to
Yes.
the Manage tab there, so you have 5 questions lined up.
Okay, sorry. IV keys changed on each encryption based on the previous block, hence the need for. Okay, so that was just a comment, I think, on where I said the IV doesn't actually need to be secured. It's something that you can transmit with, so they're just saying they believe it's changed each time that they're doing the encryption of a previous block, hence it's not needed. So it's back to the comment that IV can be sent in the clear and it's not a concern. Which hash encryption algorithms are good to use on a web farm? So I showed a couple examples since here about, again, depending on what you want to do, and if I were just taking data that I needed to encrypt safely on a web server and then give it to one of my internal systems to play with, I sure like using asymmetric, getting the public key, storing that on your web server. You don't even need to worry about encrypting or anything. Just either put it right in your code or put it in your web config because it is a public key. As soon as you encrypt with that, as long as you keep your private key internally, you wouldn't have to care about anybody having access to it. So I think that's the best approach. That works on a web farm just fine because you'd be using the same key on each machine. In other words, that public key could be the same one on all the machines. They'll all do their encryption and everything will work fine. So that's what I would do. So the question was, can someone use your public key to assume your private key value? So I think what they're getting at is if they had your public key, is there a way to figure out the private key? And the idea with those algorithms is that's extremely difficult, if not impossible, because they assume that you're going to put public keys. So if you've ever used like PGP and stuff, they've got public key rings. So your public key, some people even put them in their signatures. It's something that people are going to see. So the expectation is there's no way for someone to computationally figure out your private key based on your public. The only real risk you get into with public-private key, I kind of alluded to it. If I'm sending to someone else and they give me their public key, I have to trust that I got the public key securely, right? If somebody were able to slip in their public key and act as if it was somebody else's, I'm going to start encrypting with it, then somebody else could decrypt it. So that's kind of the only risk there. Do you have some best practices for encrypting and decrypting data stored in a database? As a web developer, when I've had to do encryption, I typically have to encrypt at the point I get it. So I'm using things like RSA with the public key, encrypt it immediately. Then I could pass it to my middle tier, put it in queues, stored in database columns. It wouldn't matter. It's already encrypted. So essentially, as soon as I receive it, the rest of the way it goes all the way through my back end is fine. It'll be secure. And then whoever has the private key, so whatever process internally needs to read that data would have the private key and be able to see it. I have not ever focused on, in particular, database level encryption of columns or any of that kind of stuff, so I don't have any more advice besides that. What type of steps would you take for managing your keys in Azure? Things like DPA, yeah. So I have not used enough Azure to actually give any formal comment about what you would do with that. Again, if you could do the public-private key, that would be best because you don't need to worry about things being in the cloud, being safe from other people accessing. So as long as you had a configuration place where you could store that public key, then you could do all of your encryption there, and then you just need to be able to decrypt it somewhere else. If that makes sense. So I don't know if we had any, it doesn't look like we had any other particular questions. Wait one more minute.
Well, in the meantime, Robert, thank you very much for a great session, and thank you everybody for joining us today. I apologize for the audio issues at the beginning, but I'm glad we got those sorted out fairly quickly.
Okay, well, again, I'm going to turn in all of the code and the slides, and feel free if you have questions after the talk, you can email me or contact me on Twitter. I'd be glad to answer any questions you have about this. I've got 2 other talks coming up. I've got one later today on Fiddler, if you're interested in Fiddler and how to use it for troubleshooting and performance evaluations and things for your website. And I've got one tomorrow on web performance, just compression, minification, techniques like that. So if you're interested, you could take advantage of those as well.
Robert, if you have time, you got one more question in the
Sure.
Q&A panel.
What is a good minimized salt size when hashing a password? I don't know that I've ever seen any particular recommendation on what that would be. Again, the larger the size, the more difficult it will be for people to gain access to it. But I don't think in the case where we're talking about, if you think about dictionary attacks, what they need to do is they would have to pre-compute basically a whole dictionary with various salts. So the bigger your salt size was and the potential size of that just makes that much more difficult. I think even with the value that I was using, people aren't going to try to do dictionary attacks anymore against your entire dictionary. They'll go after a particular password, and if you're storing that salt in the clear like they did in the Unix ones, the size won't make any difference. I mean, it'll make it potentially a little slower for them to do the hashing, but not much. So I wouldn't worry about that. The entropy stuff, again, is what I would focus on. Have some extra random data that you're going to put in there that you can store somewhere. Okay. Well, again, feel free to contact me if you have any questions, and thanks for coming.